The center of mass is a fundamental concept in mechanics, serving as a key point for analyzing objects' motion and behavior. Let's delve into the basics of the center of mass and its significance in understanding physical systems. The center of mass is a theoretical point that represents where the entire mass of an object can be considered to be concentrated. When observing an object on the screen, with a mass of m kilograms, it's important to recognize that its mass is spread throughout its volume. However, for analytical purposes, we can envision a hypothetical point, labeled as point P, within the object where all of its mass is concentrated. This point, known as the center of mass, serves as a convenient reference for understanding the object's overall mass distribution and its behavior in various physical phenomena. When discussing the behavior of an object in various physical scenarios, we're referring to how it responds to external influences. For instance, if an impulsive force is directly applied at the center of mass of an object, it will propel the object in the direction of that impulse. This movement mirrors what you'd observe if the same impulse were applied to point mass P, representing the center of mass. However, if an impulsive force is applied at a point other than the center of mass, the object's response becomes more intricate. In this case, the object will not only move in the direction of the force but will also undergo rotational motion. This means it will begin to rotate around its center of mass, while simultaneously moving along the direction of the applied force. Okay, let us calculate the center of mass of two-point objects, M1 and M2, connected by a weightless rod. We'll start by identifying a point P on the rod, where the center of mass should be. The coordinate system you see on the screen, with the origin at O, will serve as our laboratory, and distances to the masses will be x1, x2, and xcm. Now, to find the center of mass, we can use the principle that the total torque around the center of mass must be zero, for the system to remain in rotational equilibrium. Here, we'll designate P as our pivot point, and assess the torque of both weights, in the anticlockwise direction. The distances to each object, from the designated point P, are shown on the screen. The torque exerted by M1, about point P, denoted as τ1, is expressed as follows, where g denotes the acceleration due to gravity. Similarly, the torque exerted by M2 about point P, denoted as τ2, is described as shown here. Since the system is in rotational equilibrium, the net torque must be zero. Let's substitute the expressions for τ1 and τ2 into this equation, and rearrange the terms. This expression calculates the center of mass xcm in terms of masses and distances from the reference point O. In the case of a discrete particle system, this formula determines the location of the center of mass in relation to a common static frame of reference. However, it is vital to note that this frame of reference is not always static. In this expression, m refers to a point mass, independent of its size or geometry, and is a scalar quantity, whereas r is a position vector of mass m, relative to a coordinate system. Working with position vectors can be difficult, especially in complicated systems with many elements, as illustrated on the screen. To make the analysis easier, we use the x, y, and z coordinates that define the laboratory frame. Each mass in the laboratory, indicated as m sub I, has a location vector, as depicted here. We can expressing the center of mass of the system, in terms of each object's mass, and spatial coordinates. However, we can take this analysis one step further by deriving separate formulas to determine the x, y, and z coordinates of the center of mass, directly from this expression. To find the x coordinate of the center of mass, we sum the products of each object's mass and its corresponding x coordinate, and then divide by the total mass of all objects. A similar process is followed for the y coordinate ycm, and z coordinate zcm. Once we have determined these coordinates, we can express the position vector of the center of mass rcm, as a three-dimensional vector containing the calculated x, y, and z coordinates. This approach allows us to precisely locate the center of mass within the given coordinate system, considering the distribution of mass across all objects. Let's look at an example to get a better understanding of the notion of the center of mass. What you see on the screen are three flat objects with uniform density. Each object's centroid contains its center of mass, denoted as P1, P2, and P3. The masses of the objects are given as 4 kg, 2 kg, and 6 kg. The distance between P1 and P2 is 6 cm, while the distance between P1 and P3, and P2 and P3, is 4 cm. To begin, we'll set up the laboratory frame, and calculate each object's position relative to it. In the previous section, we derived an expression for the position vector of the center of mass. Similarly, we'll express the center of mass in terms of the coordinate system. The position of the center of mass from the x-axis is given by this expression. When substituting the values into this equation, it is essential to remember that distance is a vector quantity. Therefore, the sign of the distance must be correctly applied to reflect its direction in the coordinate system. So, the x-coordinate of the center of mass is calculated as -0.5 cm. This means the center of mass is positioned half a centimeter to the left of the origin, along the x-axis. To determine the y-coordinate of the center of mass, we followed a similar procedure as we did for the x-coordinate. The y-coordinate is determined to be 0 cm. This indicates that the center is located half a centimeter to the left of the origin and on the x-axis. Finally, we can express the center of mass as depicted here. This expression holds true for this frame of reference. However, if you shift the laboratory to any other location, the expression for the center of mass will change accordingly, but the position of the center of mass in relation to the objects will remain the same. The center of mass is an intrinsic property of the system, and depends solely on the distribution of mass, and the relative positions of the objects. Thus, while the coordinates of the center of mass might change with a different frame of reference, its actual position relative to the objects themselves does not. Before we proceed to the next section, let's look at another example. In this example, we have a solid uniform ball with a mass of 2 kg, placed on a small watercraft with a mass of 10 kg. Both the ball and the watercraft are floating on water, which does not exert any drag on the boat. The distance from a post on the shore to the center of mass of the boat is 6 meters, and the distance from the post to the center of mass of the ball is 9 meters. Our task is to determine the distance from the post to the center of mass of this combined system. First, we need to identify the laboratory frame. Since the distances have been given to us from the post, we will use this post as a pivotal point for our laboratory frame. By defining the frame of reference with the post as the origin, we can determine the position of the center of mass for the combined system, in relation to a fixed reference point. We'll take the same approach as in the last example, and write this expression for the center of mass in the horizontal direction. The center of mass of the combined system is 6.5 meters from the post, along the horizontal direction. At this point, we will not calculate the vertical distance to the center of mass since the information provided is not adequate to determine it. We will now allow the ball to roll on the boat's deck, and measure distances from the post again. This time, the distance from the post to the center of the boat is 7 meters, while the distance to the ball is 4 meters. Let's use the new distances to identify the system's center of mass. Interestingly, the center of mass of the entire system remains the same, at 6.5 meters from the post. This result might seem surprising initially, but it can be explained by considering the system as a whole. Even though the individual positions of the boat and the ball have changed, the overall distribution of mass relative to the post has not. The combined system's center of mass remains unchanged, because the movement of the ball relative to the boat does not alter the total mass distribution's balance point when observed from the fixed reference point of the post. This insight highlights the principle that the center of mass of a system depends on the overall distribution of mass, and not just the positions of individual components. Let's delve into a detailed discussion of this phenomenon in the next section. Understanding why the center of mass remains unchanged, despite the shifting positions of the individual components within the system, can offer valuable insights into the principles of mechanics. What you see on the screen are several particles interacting with each other. These particles can attract or repel one another, and they can also collide and break into multiple smaller particles. Essentially, within this space, anything can happen to these particles without the influence of any external force. Despite the dynamic interactions among these particles, the center of mass of the system will either remain stationary or continue to move in the same direction at a constant velocity. This behavior indicates that the total momentum of the system of particles is conserved in the absence of a net external force. The total momentum of the system can be calculated using the product of the total mass of all particles and the velocity of the center of mass. This overall momentum is equal to the sum of the momenta of the individual particles added together. This relationship can be described mathematically as follows. Regardless of internal changes in the system, such as particle attraction, repulsion, collision, or fragmentation, the center of mass follows a predictable trajectory, or remains stationary, if no net external force acts on it. This notion is critical for understanding the behavior of particle systems, and is applicable in a variety of domains, including classical mechanics, astrophysics, and others. The predictability of the center of mass provides a strong framework for analyzing sophisticated systems, and comprehending their overall motion. This concept assures that, in the absence of external forces, the motion of the center of mass remains constant, reflecting the fundamental law of conservation of momentum. When dealing with systems of interacting particles, we often refer to two different reference frames, the laboratory frame, and the center of mass frame. Understanding these frames, and their differences is crucial for analyzing the dynamics of such systems. The laboratory frame serves as an absolute reference for observing the dynamics of the system. In this frame, object locations and velocities are measured in relation to the laboratory, which is considered stationary and fixed. One of the most essential characteristics of the laboratory frame is that the system's overall momentum is conserved, both before and after an occurrence, assuming the net external force is zero. The center of mass frame, in contrast to the laboratory frame, is a reference frame that moves along with the center of mass of the system. In this frame, the center of mass is effectively stationary. This means that within the center of mass frame, the velocity of the center of mass is zero. Consequently, when the velocity of the center of mass is zero, the total momentum of the system is also zero. This implies that the sum of the momenta of the individual particles within the center of mass frame is zero. Please keep in mind that I have used the prime sign to refer to values in the center of mass frame. The center of mass frame becomes particularly useful for analyzing internal interactions and collisions. By transforming to the center of mass frame, we can simplify calculations significantly. This is because, in this frame, the net momentum of the system is eliminated, allowing us to focus solely on the relative motions and interactions of the particles. To help us understand what we discussed so far, consider a system involving two particles with masses m1 and m2, and velocities u1 and u2 in the laboratory frame. Following a non-relativistic collision, the velocities of these particles change to v1 and v2. First, we will determine the velocity of the center of mass both before and after the collision. We can begin by expressing the total momentum of the system prior to the collision. From this expression, we can determine the velocity of the center of mass before the collision. Following a similar approach, we can determine the velocity of the center of mass after the collision. In the laboratory frame, total momentum before and after the collision is conserved. Therefore, we can equate the velocity of the center of mass before and after the collision, resulting in this expression. This expression comes in handy when we have to solve problems related to collisions. You need to note that this expression is valid only in the laboratory frame, as momentum is conserved before and after a collision only in the lab frame. However, to analyze the collision in the center of mass frame, we need to transform the velocities to the center of mass frame. The formula for the relative velocity of one object with respect to another can be used to determine the velocity of m1 in the center of mass frame. Specifically, by using this relationship. In this expression, u'1 is the velocity of m1 in the center of mass frame, and u1 is the velocity of m1 before the collision in the lab frame, and u sub cm is the velocity of the center of mass. Using the same method, we can determine the velocity of m2 before the collision in the center of mass frame. Similarly, we can figure out the velocities of m1 and m2 following the collision. Taking account of these velocities in the center of mass frame, we can write this expression for the total momentum prior to the collision. As we discussed in the preceding section, the total momentum of the system in the center of mass frame is zero. This means the sum of the momenta of individual objects is zero as well. A similar result can be obtained for the total momentum of the system after the collision. This is very helpful, since the collision can be analyzed easily in the center of mass frame and then transformed to the lab frame when needed. Let's take a look at a few examples to comprehend our understanding of the section that we covered thus far. In this example, a steel rod with a mass of 60 kilograms and a length of 10 meters is on a frictionless surface. A cylindrical object with a mass of 4 kilograms is placed on this steel rod. The cylinder moves a distance of 8 meters on the surface of the rod. We need to calculate the distance that the steel rod has moved. Alright, before we jump into solving the problem, we first need to identify a laboratory frame of reference and mark all the distances. Remember that this frame remains stationary and is independent of the motion of the particles within it. So, we can take the readings from the pole next to the steel rod before and after the cylinder has moved. Next, we need to find out the net external force applied to the system in the direction of motion. You may notice that gravity is pulling both objects downward, but this is independent of the direction of motion. Therefore, the net external force in the direction of motion is zero. When the net external force is zero, the center of mass of the total system should remain fixed after the cylinder has moved to the other end. To keep the center of mass in the same position, the steel rod needs to move in the opposite direction. Let's identify this distance as x, and mark the distances to the objects from the rod after the cylinder has rolled to the other end. We will now assume that the center of mass is at a distance x cm from the post, and write the expression for the center of mass prior to the movement of the cylinder. From this expression, we can calculate the distance to the center of mass as 5.25 meters. As mentioned before, this should be the same distance to the center of mass, following the displacement of the cylinder. If we write the expression for the center of mass after the displacement of the cylinder, we should be able to calculate the distance that the steel rod should move to maintain the center of mass in the same position. When we solve for x, we find that the displacement of the steel rod is half a meter. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. In this setup, a solid block with a mass of 1 kilogram is placed on top of a triangular prism with a mass of 10 kilograms, as shown here. Due to gravity, the block slides down the inclined face of the prism, causing the entire system to slide along the surface on which it rests, until the block reaches the ground. The length of the bottom face of the prism is 11 meters, and all contact points are frictionless. We need to calculate the distance the prism shifts when the block reaches the bottom of the prism. At first glance, you might think that it is impossible to solve this problem considering that the center of mass is fixed. However, if you delve deeper, you'll notice that the directions of the gravitational force and the normal force are perpendicular to the motion of the system. This means the net force in the direction of motion is zero. Therefore, the center of mass measured in the direction of motion should remain fixed as the block moves. As before, we will first identify a reference point from which to measure the distances to each object in the system. Note that the distance to the center of the prism, referred to as d, does not need to be known in absolute terms, as knowing the actual distance is not necessary to determine how far the prism has shifted. The expression for the center of mass xcm, of a system consisting of two masses m1 and m2, with their respective positions x1 and x2, is given by the formula on the screen. We will substitute the given quantities, and derive an expression for the center of mass of the complete setup, before the block starts to move. When the block reaches the bottom of the prism, let's assume its position is x distance away from the reference point. We will write the expression for the center of mass, when the block is at the bottom of the prism. The center of mass, when the block is at the bottom of the prism, must equal the center of mass, when the block was at the top of the prism, because the horizontal component of the center of mass is conserved. Setting the initial and final center of mass positions equal, we obtain this expression. When we solve for x, we find that the distance displaced is 1 meter to the right from the reference point. We will now move to the next section. Here, we will understand how the system behaves when a net external force acts upon it. In the preceding section, we derived the expression for the total momentum of the system. When no net external force is applied to the system, its momentum is conserved. Therefore, the derivative of the total momentum is zero. However, when a net external force is applied, the momentum of the system in the direction of the force is not conserved. We can express the rate of change of momentum as follows. The momentum of an object can be changed only by applying a force, according to Newton's second law. Therefore, the change in momentum of the center of mass can be expressed as follows. This shift in the momentum of the center of mass equals the cumulative change in momentum of all particles within the system. Essentially, it is the vector sum of the forces exerted on each object within the system. Initially, this might not be immediately obvious, but it becomes clearer upon deeper reflection. When an external force acts on a system of individual objects, the center of mass, treated as a point particle with the total mass of the system, reflects the collective behavior of all the individual masses within the system. This suggests that the dynamics of the system's center of mass can be studied as if all the mass were concentrated at one point, influenced by the collective impact of all external forces. This simplification enables us to envision the motion of the system's center of mass, using the principles of Newtonian mechanics, making it a potent method for analyzing the behavior of complex systems. To elaborate on the concept we discussed, let's consider an example, where a particle with a mass of 2 kilograms is projected with a velocity of 15 meters per second, at an angle of 30 degrees to the horizontal. Due to an explosion at the highest point of its trajectory, the particle breaks into 2 pieces of equal mass. One piece falls directly downward, while the other piece acquires a horizontal velocity, and lands some distance away from the point of projection. We need to determine the distance from the point of projection, where the second piece lands. Let's consider a scenario where the projectile continues its motion without exploding. In this case, it follows a predictable path, typically a parabolic trajectory, due to the force of gravity, and lands at a distance from the point of projection. Let's assume that this range is 2L. For simplicity of calculation, we take the mass of the projectile as 2m. When the projectile is in motion without an explosion, the only force acting on it is gravity. Using Newton's second law, we can express this force as follows. Since there is only one object in this system, this is the net force acting on the system. The trajectory of the projectile is determined by this gravitational force, resulting in a parabolic path. The range can be determined using the kinematic equations for projectile motion. Now, consider the scenario where the projectile explodes at the highest point of its trajectory. After the explosion, one particle falls straight down, and the second particle acquires a horizontal velocity. At this instant, we have two objects within the system, each subjected to gravitational pull. Using Newton's second law, we can write the following expressions for the gravitational force acting on the two masses, each with mass m. Adding these two forces, we find the net force acting on the system, following the explosion is given by this expression. From what we discussed in the preceding section, we know that the behavior of the center of mass is crucial. Despite the explosion being an internal event, the center of mass of the projectile system will continue to move as if the explosion never occurred. This can be quite counterintuitive, but illustrates the importance of the center of mass in simplifying complex physical problems into more manageable analyses. The overall path of the center of mass is influenced only by external forces like gravity, not by internal forces, such as those present in an explosion. Therefore, the center of mass will follow the same parabolic trajectory it would have if the explosion had not occurred. This means that if the range of the projectile without an explosion is 2L, the center of mass of the system after the explosion will also follow a path that lands at the same distance from the point of projection. In essence, before the explosion, gravity is the sole external force acting on the projectile, resulting in a downward acceleration. Newton's second law allows us to quantify this acceleration, as it relates to the mass of the projectile, and the strength of gravity represented by the gravitational constant, g. After the explosion, assuming no other external forces intervene, the second law confirms that the acceleration due to gravity will continue to act on the center of mass, in the same manner, thus the motion of the center of mass will remain unaffected by the internal forces of the explosion. This principle provides a powerful tool for solving this problem, as it enables us to predict the subsequent motion of objects after a collision or explosion. In our exercise, it assures us that the center of mass for the projectile will continue to move with the same velocity in the horizontal direction, even after the explosion. The internal forces of the explosion have no power to alter the horizontal component of the momentum. We will consider the point of launch as the reference point, and apply the law of conservation of momentum to the system, after the two particles have landed. Let's denote x as the distance from the point of reference to the furthest particle. Since momentum is conserved in the horizontal direction, we can write the following expression. We can calculate the distance to the furthest point by solving for x. This is approximately 29.8 meters. In essence, external forces are forces that originate from outside a system, and can alter the system's total momentum. Typical examples include gravitational pull, friction, or a push or pull from an object not part of the system. In projectile motion, the primary external force is gravity. It acts continuously on the projectile's center of mass, and determines its trajectory. Distinguishing between internal and external forces is crucial when analyzing physical situations. Internal forces, such as the explosive forces in our projectile example, can change the shape or distribution of mass within a system, but do not affect the overall motion of the system's center of mass. The motion of the center of mass of our projectile post-explosion is a perfect demonstration of this principle. Despite the internal upheaval, the path of the center of mass remains uninterrupted, because no new external forces have been introduced. With that example, we conclude our discussion on the center of mass. Thank you for watching this video all the way through. I hope these examples have helped you understand the concepts of the center of mass, and conservation of momentum, and how Newton's second law applies to a system of objects. In our next video, we will explore another fascinating topic. If you haven't subscribed already, please consider doing so to stay updated on future content. Until our next video, take care, and goodbye.